Hello, everyone. Welcome to another episode of Q&A about history of science and technology. And I see all kinds of saved up questions here, so let me see what I can address. There's one from Lola here. Are the stars and constellations we see today the same that were seen by ancient civilizations who first studied them? Do star positions ever change? So that's kind of a combination of history and science. So first question is about star constellations and their positions. So there is so-called proper motion of stars, which means stars do move around. The stars which are closer to us, we notice their motion more than we notice the motion of stars further away. There are some stars that are pretty bright because they are intrinsically, their absolute magnitude as stars is very high. And even though they're a long way away, the fact that their absolute magnitude is high means that their relative magnitude, the perceived brightness of those stars, is still pretty high. So when we see a constellation, there could be 10 stars in the constellation, and some of them are very near to us, and some of them are very, very far away. The ones that are very far away, we're unlikely to see motion in. The ones that are near us, we will see motion. So for the nearest stars, there's definitely visible motion that's happened, for example, since antiquity to today. And there are definitely some changes. In fact, in Wolfram Alpha, remember we put in the data on proper motion, and you can actually see constellations at different times in history there. And there are sort of random stars in a constellation that will move around because they happen to be closer to us. Now, in terms of, so yes, there are some changes there. There's also one of the questions that's a sort of a typical history of science question is Hipparchus made a star catalog. Ptolemy made a more famous star catalog. I think Ptolemy's was like in the 1st century AD. Hipparchus's few centuries BC. And they were and so one of the questions that's been around in history of science for a long time is, did Ptolemy plagiarize Hipparchus? And the thing that you might be able to tell is if the stars would have moved between the time of Hipparchus and the time of Ptolemy, would that be a giveaway that Ptolemy just plagiarized Hipparchus's star catalog? And the answer is actually one of my kids, Christopher, actually did some work on the kind of the detailed statistics of kind of the star catalog of Ptolemy versus Hipparchus. And as I recall, the conclusion was it's kind of on the edge. You can't quite tell. It's kind of like from the information available, it's like, yeah, Ptolemy could have got his stuff from Hipparchus and the stars could have moved slightly over those couple of hundred years, or he could have observed them separately. But it was kind of not obvious. But so in terms of, so now the next question is, if you look at the constellations that we have today and that we pick out, whether it's, the constellation, I don't know, Cygnus, Virgo, whatever, all the various constellations, the signs of the zodiac, the make these constellations, do we pick out the same sort of patterns of stars as people did in ancient times? Well, we inherited the Babylonian constellations. The constellations that we have were basically picked out by the Babylonians. In ancient China, for example, different constellations were picked out. Just, which stars went with which stars, just completely different. It's kind of an interesting test of kind of the perception of things by different civilizations of, you've got this random array of stars. How do you join the dots to pick out different kinds of critters? And obviously the constellations that we have now are ones that, are things like, water bearers and things like this, which are fine things of antiquity, not so commonly seen in most parts of the world today. I actually don't know, for the southern stars, I actually don't know where the constellations, which civilization picked out the constellations of the stars that can only be seen in in the southern hemisphere, because that obviously wasn't the Babylonians, because they didn't get to that part of the world. So I don't know exactly how that worked out. But yeah, so I think that's the story of that. And I mean, we know that many aspects of the stars that we have today will have moved. Polaris, well, will it be the North Pole star forever? No, it's moving. And other kinds of features of, the Big Dipper, or what in British English is called the Plough, that constellation of stars will not have the shape it does at some time in the future. Now, there's also another effect, is the precession of the equinoxes, the fact that the Earth is precessing like a top on its axis. It's 23-degree tilt relative to the plane in which it orbits the sun. There is precession of that every 23,000 years, I think. And so that's a substantial difference in the constellations that we see in a particular place in the Northern Hemisphere, for example, from in antiquity, because that's, antiquity is now, let's say 3,000 years. That's a decent fraction of the rotation period of the precession of the equinoxes. So that's another phenomenon. I mean, in terms of what will be seen in the past, what will be seen in the future, if you go back to really ancient times, things like, there's the question of, will eclipses work the same way? I mean, right now, a total solar eclipse, there's this sort of remarkable fact that the disk of the moon more or less exactly covers the disk of the sun. Clearly, if we were living on Mars, for example, the couple of satellites, Phobos and Deimos there, their sizes relative to the disk of the sun, they're tiny relative to the disk of the sun in that case. The moon, in general, in our solar system, our moon is a very big moon relative to the size of our planet. And but it's gradually getting further and further away from the Earth. So eventually the moon, the disk of the moon, will no longer cover the disk of the sun when viewed from the Earth. But in the time of the dinosaurs or something, there will be, you could have many, it will be much easier to have a total eclipse, because the disk of the moon was much bigger relative to the disk of the sun, because the moon was proportionally closer to the Earth, which will have led to all kinds of other effects about tides and all sorts of other features. And in a sense, the reason the moon is getting further away has to do with the fact that there is some tidal deformation that is slowly, energy is being dissipated by that. Anyway, let's see. Let's see. Andrew is asking, what do you make of the relationship between rhetoric and math? They're held in contradistinction, but I'm thinking the relation between rhetorical invention and Greg Chaitin's idea of math creativity. Boy, I'm not completely sure. I've known Greg for like 40 years quite well, but I'm not sure I know exactly what his idea of math creativity is, but maybe I can guess. It's worth remembering rhetoric. Back in antiquity, people would study rhetoric. They would study, that was, well, in the Middle Ages, it's kind of rhetoric, logic, math. These were things that were studied as a mechanism for this idea of, there is a definite pattern to arguments that you can give, which is some part of the story of rhetoric. That became a that idea of the patterning of arguments is what Aristotle turned into logic. Aristotle kind of lifted this formal structure of logic out of the repeated patterns of rhetoric that he saw. I'm not sure. I mean, in a sense, logic is a formalization of rhetoric. Math is another thing that you can kind of lift out of language. I mean, we could say, just as a matter of plain language, if I've got 2 ducks and a duck, then I'll have 3 ducks. And I can say that just linguistically, but then I can kind of lift out of that this 2 + 1 = 3 kind of formal structure. what math did was it built this very tall tower of formalism on top of what would otherwise be just kind of linguistic statements. And that's been the typical story of science, particularly post the 1600s, is this idea of, can we make this kind of precise rule-based structure that kind of ascends above the things that we can describe in ordinary language? I mean, if you look at theories of physics, for example, from antiquity, they were always described in ordinary language. It's like, the atoms, the void, the this and that and the other. These were just matters of ordinary language. Nobody was saying, and then we have this precise kind of mathematical structure that represents an atom or represents the void. If they had done that, many things that were discovered only many, many centuries later would have been discovered back then. But at the time, the way of describing the world that people imagined was a linguistic narrative way of describing the world in terms of words. And this idea of a formal way of describing the world, that really was something that I would say arose in serious terms in the 1600s. Now, there have been some precursors of that. For example, with geometry and Euclid and so on, there was this idea of a formal triangle or something, different from the actual triangle that you might draw in the sand or some such other thing. The idea that there was a formal version of that, and that's something that Plato and other people were very into, this idea of a kind of a formalization of things that they saw, particularly in the case of geometry. Geometry was the place where there was first this idea of sort of idealization of things as the ideal triangle as opposed to the actual triangle and so on. Now, I think, the notion of the extent to which, you talk about things in the world, you write factual texts, you write fictional texts. The concept that you could write a fictional text, or you could just write about anything, that's a question of to what extent does that map into our thinking about math? And that sort of has to do with the question of, relates to the question about whether math is invented or discovered, this whole set of questions about whether we can just make up math about anything, or whether math is somehow tied to something about either us or about the world in which we live. I think that's been greatly clarified by things I've done in recent times about the physicalization of metamathematics, but we can kind of go through a little bit of that. I mean, so Euclid, for example, in his time, he thought his geometry, he did arithmetic and things as well, he thought those were things where they were kind of sort of formal abstractions of things about the world. When he said, two parallel lines will never cross, he was imagining two lines that you would actually draw in the sand, and they would actually never cross. And I think much as Aristotle was imagining as he talked about logic of P and Q and so on, not that he quite did it that way, but that's the modern version of it. He was thinking about that as it's really a sentence in Greek or whatever, but there are these pieces of it that you can identify in this kind of formalized way. So, back in those days, the idea was take the world as we experience it, whether it's natural language, whether it's geometry of things drawn in the sand and so on, and abstract from that something which we can discuss in a more formal way, in a way that doesn't depend on the details of whether the stick that we used to draw the thing in the sand was big or small or whatever else. So that was kind of the idea of how mathematics would this sort of abstraction of the real world. Then we go 2 millennia later, and we go to the 1800s, and we go to the early 1800s, when people were starting to say, well, wait a minute, do we really have to build math that way? So, for example, do parallel lines ever cross? Lobachevsky and so on in the 1830s, I think, was starting to say, no, we can actually imagine a space where parallel lines do cross, and a curved space where parallel lines cross. This thing about parallel lines not crossing is really just an axiom that Euclid is choosing based on the experience of the world as the world exists. It doesn't have to be that way. Similarly, Galois, same time, 1830s, talking about things like group theory, where it's like, well, normally we have, A times B equals B times A, but if these are elements of this abstract group, that commutativity property doesn't have to be true. Same with Hamilton talking about quaternions, same around the same time, same issue. And then soon thereafter, George Boole, talking about Boolean algebra, another example of where we have something that's sort of qualitatively like ordinary algebra, but it doesn't behave. Ordinary algebra is an abstraction of dealing with numbers, but this has the kind of the character of algebra, but is not about ordinary numbers because things aren't commutative and you have different rules and so on. So that kind of turned into, by the 1870s, 1880s, people like Gottlob Frege saying, well, wait a minute, what really is mathematics? What is, is it just an arbitrarily chosen set of axioms that we then propagate forwards with rules? And, Frege had the interest in saying, well, is it really the case that what's underneath mathematics is just logic? And then we put on top of logic certain assumed axioms from which we can build anything we want. And then that kind of, there were other people involved. Giuseppe Peano was another person. And then David Hilbert, sort of a big figure in the late end of the 1800s, who kind of really had this idea that mathematics should be a formalized thing where it's just you write down axioms, you prove theorems. Hilbert's big break in, I think, 1870s, his sort of first big discovery was a non-constructive proof. So normally when you make proofs, you say, there's this possibility, there's this thing, but if you say this thing can exist, you can, in a constructive proof, you can say, and here it is. I can show it to you. The number 13 has this property. But Hilbert gave a proof which was non-constructive. That is, he could show that something was true without ever being able to produce the thing that made it true. And at first, people were very surprised by that, but that was kind of the beginning of Hilbert's approach to this formalistic way of doing mathematics. So by 1900 or so, Hilbert was talking about the idea of, well, mathematics is just you specify rules and you just go forward with those rules. And he said, we could define a mathematics in terms of tables and chairs. Doesn't matter. It doesn't have to be numbers. It doesn't have to be this, just a formal set of rules. And so this was the idea that he kind of had this notion that there was a mechanical way of deciding everything, of solving the so-called decision problem, of making any mathematical statement be something that you could just mechanistically decide from the underlying axioms of mathematics, which, by the way, he implied you could just pick the axioms however you wanted. Now, then Gödel came along in 1931 and showed that this idea that there was a mechanical way to get to any theorem of mathematics in a finite number of steps, that wasn't true. That was the point of Gödel's theorem. That turns into, in modern times, computational irreducibility and lots of other ideas, that there isn't a finite path necessarily, even given that you know the axioms. There's no guarantee that a particular theorem is inaccessible. There might always be a longer path to reach that theorem. There's no upper bound on how long a path you might need. Now, Gödel, part of his reason for coming up with Gödel's theorem was he wanted to blow up Hilbert's idea of a formalistic mathematics. He believed more in sort of Plato's idea of mathematics, that there is some true mathematical reality. There's a concrete thing that is mathematical truth. And we, when we do mathematics, are merely discovering that abstract concrete truth. That mathematics isn't in Euclid's, in Gödel's view, or Plato's view, that mathematics is its own thing with its own reality, having nothing to do with the particular details of our physical universe and so on. So Gödel, in sort of blowing up Hilbert's program, kind of had the idea that he was going back to a more Platonic view where there is a real existing thing that is mathematics, which we with our human brains and so on get to sample pieces of. Okay, so segueing to much more modern times and the results of our physics project and the idea of this thing we call the Roolead, which is the entangled limit of all possible computations. And that one of the things that, this is now a couple of years ago, this idea that within the Roolead, within the entangled limit of all possible computations, are all possible mathematical theorems and all possible proof paths for all of those theorems. And the question is then, what do we do when we do mathematics? Well, what we do when we do mathematics is we're essentially sampling that Roolead. We are observers of the Roolead as, when we do mathematics, sampling pieces of what exists out there in this limit of all possible computations. Okay, the really interesting thing is that Roolead is the same thing that underlies physical reality. As physical observers of the universe, we're doing the same kind of thing. We're sampling a little piece of the Roolead that corresponds to our physical characteristics as observers and experiencers of the universe. So the really surprising thing that kind of surprised me is the realization that physics and mathematics are at the lowest level the same thing. They're both made of the Roolead. There is only one Roolead. And if you believe that the physical universe exists, whatever sense you believe the physical universe exists, so also the mathematical universe has to exist. And then the question is, well, are the laws of physics, how do they depend on our character as observers? This is something I've worked on a lot, that the fact that we observe physics the way we observe physics to be with gravity and quantum mechanics and so on is a consequence of the fact that we are observers who have the characteristics that we have. We're computationally bounded, we believe we're persistent in time, those kinds of things. That characteristic of us as observers implies that we must experience the laws of physics as we experience them. But that characteristic of us as observers, what underlies the physical world is this Roolead, which has all these possibilities in it. But the way we sample the Roolead is such that we must observe the laws of physics that we observe. So what does that mean for mathematics? What it means for mathematics is we are mathematical observers with the same kinds of constraints. We have finite minds, et cetera, et cetera, et cetera. We have to experience mathematics through our finite minds. That puts constraints on the ways in which we can sample the Roolead. In effect, it puts constraints in the end on the kinds of axioms that we can attribute to mathematics and have us humans be able to coherently do mathematics. It could be the case that we would make up these axioms, and every time we wanted to conclude something about mathematics, we'd have to go down and be grunging around at the very axiomatic level. That's not how mathematics actually works. There's a higher level experience of mathematics. It's kind of like we can experience not the molecules bouncing around in the room, but the air currents. It's the same kind of thing in mathematics. We can experience not the very low level subaxiomatic foundations, but instead this kind of higher level aesthetic kind of thing that is the level that mathematicians typically experience things at. And the fact that that's the level we experience things at is a consequence of our characteristics as observers. So it ends up being the case that I don't think it's true that there are arbitrary axioms that we might choose. There are axioms which, if we chose them, we wouldn't have a coherent view of mathematics. Mathematics would kind of get shredded. And I think there are probably things that, and so this question of sort of to what extent can we just go off and just pick mathematics at random? The answer is there will be constraints. There may even be constraints that we're seeing right now of sort of questions like the continuum hypothesis, which is an axiom that you kind of seems like you can take it or leave it, but that's probably not true. It's probably the case that one branch of that is the one that leads to kind of human sort of sampleable mathematics and another does not. So that was a rather long and technical discussion of that point. Let's see. Yes, there was a comment from Jimmy here commenting on my earlier answer about whether the heavens, the stars and so on, are the way they are, the same way as they were in antiquity, and commenting on novas and comets and things. I would say that the supernovas, stars exploding, definitely a change. The Crab Nebula in 1054 was one example of a star that I don't know how bright that star was before it exploded. I mean, when it did explode, I think it made the night sky bright for like 3 days or something, and it was kind of hard to miss. I think there are in the next 10 million years, there are some fairly nearby supernovas that will happen, but the timescales are pretty long. I mean, there could be a supernova next week. We wouldn't know it. But it's not something where any of the really nearby stars to us is going to do that kind of anytime soon. I mean, if we look at other galaxies, we certainly see supernovas, but that's not something you see in the night sky relevant to constellations and such like. The question of comets, that was wandering stars and so on, that was a very critical piece of the surprise of the kind of the constancy of the heavens. I mean, the fact is that this idea that the heavens are perfect and constant is an important kind of foundational idea in both mathematics and theology in antiquity. And the fact that things like that the figure of the moon or the sun is a perfect circle, that was something where that notion of perfection was important in the view of kind of the ethereal realm as distinct from the realm of the of things, terrestrial things and things created by humans, which have this imperfection. And I wouldn't be surprised if some of the thinking about theological kinds of ideas really was a consequence of the fact that, gosh, you can look up in the sky and the moon is a perfect circle. And that's that sort of perfection in the heavens is something that probably played quite big in the kind of the view of a realm of kind of things above what we humans can do. But and so when a new star showed up as a comet or something, that was kind of a big deal. And obviously there are things like Halley's Comet, which had a storied history. I mean, it was I think it showed up when William the Conqueror was conquering England in 1066, and or maybe when he was. I know it's in the Bayeux Tapestry, which is a sort of recording of the history of the Norman conquest, and that it shows up in some. I forget when it's actually when sort of William was going to England, or whether it was right before. But anyway, it shows up, and then Edmund Halley was a kind of statesman and science-interested statesman in the late 1600s. And that comet was named after him. And one of the things that was of great interest in those days was to explain comets. What were they? What was did they have orbits? How did their orbits work? And that was one of the big things that Isaac Newton did that led eventually to his Principia Mathematica, was explaining the motion of particularly Halley's comet. And that was significant because Halley was at that time, I think, the president of the Royal Society in England, and was persuaded, told Newton, you really have to publish all this stuff you've been doing about what amounts to calculus and thinking about celestial mechanics and so on. And that's what became in 1687 Newton's Principia Mathematica, mathematical principles of natural philosophy. Flo asks, is the motion of the moon measurable compared to human history? Certainly not by the naked eye. It's a small effect, and I don't know whether. Well, let me see. I don't know whether, since telescopes were invented, I doubt that you can tell it with the telescopes that, the span of the invention of the telescope was 1608 or so. And to now, I don't think that's measurable visually. I mean, the position of the moon is known very accurately, particularly because of the lunar laser retroreflector left by the Apollo astronauts on the moon. It's a thing that's like a street light, the street sign, basically. It has these little, well, they're not so little in the case of the lunar laser retroreflector, but they're these little glass beads, spherical glass beads, where light comes in, it's totally internal reflected, and it goes back out the same way, like a mirror, but does better than a mirror. So when you shine a laser at the moon, you shine a laser pulse at the moon, and you do timings of how long it takes to reach the retroreflector and come back. The position of the moon is known to within millimeters, maybe now. I think it's 1 part in 10 to the 15. And so I'm sure you can see the receding of the moon in that detailed data from the lunar laser retroreflector. But I don't think I really doubt it's visible in the way that one could have got in the 400 years or so of telescopic observations. Let's see. JR asks, how will history be able to correct the continuous conundrum of the accuracy of forefathers' discoveries, inventions, ideas? How can we preserve this? I think maybe what you're asking is the people get things right, people get things wrong. What's remembered in history? And do we get to learn from the mistakes of intellectual history as we might hope we could learn from the mistakes of things like socio-political history. I must say that it's always I'm something of an enthusiast of history, and it is remarkable the extent to which history sort of repeats itself. I mean, I'm always interested when there are things about technology and what's happening now and what are these companies going to do? How's this technology going to develop? It's like, let's look at an analogy. Let's look at how this relates to something that came before. Let's look at the fact that, people had electricity for 60 years or something, and they had always thought that it would be possible to transmit the human voice over an electrical line and hear it at the other end, but only when Alexander Graham Bell came along in the 1870s did that finally, with surprise, did that actually start to work. And that's very much an analogy to what's happened with machine learning and neural nets, of when we'll have a fluent kind of producer of English essays, which we have now with ChatGPT. When would that happen? When would the Alexander Graham Bell moment for neural nets happen? It's a very much analogous kind of thing. And again, like the telephone, where it was really a question of, oh, you as a human were listening at the other end. Could you understand what was being said? It's not a perfect rendition of, there's no perfect answer of what well, nowadays we know a little bit better with signal processing and so on. What will it take to be able to have the speech be comprehensible at the other end? But it was something which in those days, it was kind of much more of a we don't really know what's going to make the speech comprehensible. We're not going to be able to get every detail of the waveform. Which parts of it are going to be important? Same thing with ChatGPT. Are we going to be able to get the big picture of how the English text is produced? But, I think it's like, the statement that's often made about political history, history is written by the victors. When things have happened and it's all quite messy, and then in the end, it's the glorious revolution of some kind, and then the victors take over and you don't hear about kind of the messiness and what was on the other side and so on. That does happen quite a bit with scientific history and technological history of, you only remember the stuff that was right, you don't remember the stuff that was wrong. I think that it is very educational to understand what was wrong. And sometimes the herd of scientific or intellectual kind of belief very much went in the direction of something that was just complete nonsense. And, I think we will see that, we'll see that in all sorts of places where kind of there are several that I personally have been deeply involved in. I mean, one is the continuity of space. Something's been believed for a couple of thousand years, but it almost got to the point around the beginning of the 20th century where people said, no, space is going to be discrete, but it wasn't quite ready at that point. But then by the time we got to the, the beginning of the 2000s, for example, it's like, yep, space is discrete, space is continuous, say, sort of most, essentially all working physicists. How can it be anything other than continuous? We know space is continuous. We know it's continuous since Euclid. Turns out that's not true. And that's something which kind of was an incorrect kind of herd belief that persisted for a long time. I mean, I kind of the realization that Euclid's fifth postulate, the fact that parallel lines don't cross, wasn't right, and that could be something relevant to the theory of physics, which is what Einstein realized in 1915 with general relativity and curved space and so on. That the incorrectness for the physical world of Euclid's fifth postulate is what led to general relativity. What I realized is that the very first thing in Euclid, the very first common notion, a point is that which has no part, rough translation from Greek. A point, there is the notion of an indivisible point, and you can kind of densely put them in space. That's wrong. Just like it will be wrong for some fluid like water. There isn't a piece of water at every point. There's molecules dotted around, and so it is with the structure of space. And yes, it will be 2,000 years that people have sort of not realized that. I think it's now pretty clear from our physics project that that's the way things are going to go. I think it will be super exciting, and I'm hoping in the next few years this will happen, that we will actually see experimental evidence of the discreteness of space And then it'll be like, then after that, when that history is rewritten, there will come a time when nobody discusses the fact that for 20 centuries, people were convinced that space is continuous. And in the last century, quite intensely so. And that will be gradually forgotten, I suspect. Just as, well, for example, a good example I was studying recently is the theory of heat, the caloric theory of heat, the idea that heat is a fluid that suffuses substances. Nobody's heard of that theory today. They've heard of calories because that was a word derived from the caloric theory of heat. But the caloric theory of heat is not a thing that is discussed or taught or whatever today. It was a wrong theory. And it is interesting to analyze that theory. It's interesting to see the kind of analogies of that theory with, for example, my favorite is dark matter, where people say there's something funky about the rotation curves of galaxies. There's something funky about the way the gravity acts in galaxies. Oh, it must be particles, because that's the only thing people have seen that affects gravity is the presence of matter and particles and so on. And so, I think dark matter, just like it turned out heat was a feature of the structure of matter, the motion of molecules and so on, that wasn't imagined at the time when all you knew about was sort of fluids suffusing things. So similarly, dark matter, I think, is the same type of story. It really isn't particles. It's something about the structure of space, some feature of the structure of space, and perhaps the discrete structure of space that we haven't known before. Let's see. Paula is asking, how did early civilizations explain supernovas? Did they understand it was a star exploding? How'd they come to this conclusion? They absolutely did not know it was a star exploding. Absolutely not. I don't think, gosh, I don't know what they said. I mean, there are sort of somewhat apocryphal stories about eclipses, which were another bizarre thing, because eclipses are pretty rare on the Earth. Because of the Earth, the orbit of the moon is tipped relative to the orbit of the Earth around the sun. The moon doesn't line up with the sun very often. It only does it in very occasional times when it happens to sort of when the stars line up, more or less. Well, the moon and the sun line up, but it's a rare thing. On other planets, because the plane of the rotation of the moons is not so different from the plane of the rotation of the planet around the sun, there will be sort of eclipses much more often, although they won't be as dramatic as eclipses on Earth, because the disk of their moons is not nearly as big relative to the disk of the sun from their surface. But in any case, there's a story that Thales, one of the early Greek, perhaps the earliest Greek scientist was predicted the eclipse that would happen in a battle between the Greeks and Persians, I think. And while the battle was going on, Thales had said, there's going to be an eclipse. And all these people were out battling with each other. And then the sun got covered and everybody freaked out. And they said, they ran away from the battle. And so people gave, at least in the story is that was predicted by Thales. Now, what he probably did predict are these things called Saros cycles, which are the times when eclipses can happen. There are certain times when eclipses can happen and others when they cannot. It is not guaranteed for the Earth that an eclipse will happen at every point, at every sort of piece of the Saros cycle, but eclipses can happen then, and that's probably what he knew about. We know, for example, the Antikythera device from around 0 BC, little mechanical computer that we have, that did have a representation of Saros cycles. So that was a known thing. Maybe not in the time of Thales, obviously, but I would not be surprised that Thales knew about that. I think, and in fact, Ptolemy knew about it as well, because in Ptolemy's almanac, he discusses the kind of, in those days, people would talk about astronomy and they would prove theorems about astronomy. So, for example, Ptolemy proved the theorem that there cannot be more than, 5 eclipses in a year, I think. That purely by the geometry of the Earth and the Moon and so on, there can't be more eclipses than that. Now, Ptolemy was operating on an Earth-centric system where everything went around the Earth rather than going around the sun, but the theorem about eclipses doesn't depend on that. In fact, very little depends on that. It's really just a change of coordinate system to say things are going around the sun rather than the sun is going around the Earth. At the time of Copernicus, that seemed much more striking, but in terms of the mathematics, it's not as different. In any case, I think, let's see. So I think by the time of Ptolemy, they did know what eclipses were. I think in the time of Thales, maybe 5th century BC or more, they didn't know what I don't think they knew what was going on in an eclipse. I think that, Thales had this theory that it's often quoted as everything is made of water, which sounds kind of silly, but the very non-silly thing that he concluded was maybe, in fact, the world is made of discrete things like atoms. Democritus and the Epicureans were the real ones who talked about atoms, but the world is all made of different configurations of the same thing. And that's what we now believe from our physics project of sort of it's all hypergraphs and atoms of space. And that's sort of a one thing that everything in the world is made of. And that's something Thales figured out. In terms of supernovas, the supernova of 1054 was observed, I think it's recorded in Chinese sort of government literature. I forget, they had a name for it. Guest star, perhaps, something like that. They had a name. I don't think they knew at all what it was. And the concept of stars as being something like our sun, that was a thing that people were talking about for sure by the 1500s, 1400s, certainly by the 1600s. I think Giordano Bruno, who came to a very sticky end at the hands of the Catholic Church, actually, was notable for having said that, yes, the stars are like the sun, but far away. But I don't think that was I'm not sure that was a known. Gosh, was that something that was talked about in antiquity? I'm not sure, don't know. But the notion that a star could explode, as opposed to the fixed stars, which were in fixed positions and everlasting stars, I think it will be sort of shocking that the idea that a star would explode. Now, when did supernovas get understood? Novas, just sort of a star absorbing a bunch of gas and sort of belching it out. Those were, I think, those were well studied by the early part of the 20th century. Supernovas, it's the first one that was observed through telescopes. That's a good question. I'm not sure I know the answer to that. The study of supernovas and how they work was a thing of kind of the 1960s, I would say. The notion that stars were powered by nuclear fusion had to wait for people to understand nuclear fusion. That was the 1940s. Soon thereafter, people understood that stars were powered by nuclear fusion. People hadn't known what powers the stars. And once that was known, the idea that there could be a catastrophic collapse of a star and a supernova, that was a thing known by the 1960s. But then the question of computing the details of supernovas, that was a big, complicated mess, because supernovas are complicated. They involve many different isotopic species, many different types of atoms. They involve nuclear reactions. They involve the probabilities of different kinds of atoms colliding. A lot of those things started to be measured in the 1940s in connection with particularly the nuclear weapons program. And what ended up happening by the 1970s, there was kind of the same kind of calculational methods that were used to calculate nuclear weapons explosions were the ones that were going to be used to calculate supernova explosions. And there was typically a parallel sort of track. At the US national labs, there was interest in, like at Los Alamos National Lab, there was interest in supernovas, and there was interest in nuclear weapons. And they were kind of the same codes that were being used because you needed to use the same things. And sometimes there's a lot of complexity because some of the measurements that were being made of nuclear cross-sections, probabilities for nuclear interaction, were classified because they were relevant for figuring out things about nuclear weapons. And so you kind of maybe sort of couldn't or could use them for supernova codes. The other big problem was, for a long time, people would compute supernovas. This was still happening in the 1980s. People could compute sort of the collapse of a star. the ignition of oxygen burning, silicon burning, these kinds of things where you start getting these extranuclear reactions happening. And by golly, according to those calculations, stars wouldn't explode. And that was kind of embarrassing, because what happened in the 80s, in the early 80s, the nuclear test ban treaty came in, and that had a big effect on what one could do in terms of nuclear weapons, because before that time, you would, dig this hole in the Nevada desert, or in the 1950s, you would go to some island in the Pacific and you would detonate a nuclear weapon and you would see what happened. And you would put all kinds of instrumentation, you'd measure all kinds of things. You'd know if we built a bomb this way, it would blow up. And you had reasonable confidence of that. But by the time the test ban, what was that, 1984-ish or so, was in place, by the time the test ban came in, you couldn't do those tests in the US and so on anymore. And so that meant that it was really important that you be able to calculate, will this bomb actually blow up or not? And so then it became really a critical thing, because the same code was being used to compute would supernovas explode, and it said they wouldn't. And so what really happened? Well, they're very complicated codes. And I think in the end, and this is one of these stories which I really should check more carefully, and it's something I've heard from multiple people who were involved, and I haven't completely triangulated about the accuracy of this, but I believe that what in the end came to light is that some neutrino opacity data cards had been mistyped, and that was why the conclusion supernovas don't happen was come up with. And once that was corrected, supernovas could happen according to these codes. Now, it's a messy situation, because we know supernovas happen. So if you run this code and it says supernovas don't happen, you go keep searching for a bug until you find out that they happen. Once you find out they happen, you say, great, supernovas happen, we're done. You don't go searching for other bugs. So I'm not sure exactly how that's kind of validated. But that's kind of the modern version of sort of the happening of supernovas. There are still other kinds of mysterious things, the blazars and the gamma ray bursts and so on, where one's only just starting to have some idea of what those might be. And quasars, for example. Quasars were discovered in the 1950s, I think. Very bright radio galaxy they must have been the 1950s, because that was after the discovery of radio, the invention of radio astronomy by Jansky and people. Very kind of intense, galaxies where, the original theory for what quasars were was they were probably anti-galaxies annihilating with galaxies, because people didn't know. It wasn't clear until the beginning of the 80s, actually, that the universe didn't have equal amounts of matter and antimatter, but just separated into different pockets. That became clear, when I worked on this in the end of the 70s, beginning of the 80s. So, Pab asks, saying the stars are like the sun but far away. When that was said for the first time, other people must have thought that was crazy. How often were ideas like this disregarded at first? And how did researchers convince society of their findings? I mean, the history of science is full of people realizing things and nobody believing them, whether it's the existence of germs, whether it's the fact that the stars are like the sun, whether it's lots of these things. It's, what people say. I remember I was asking the chap who invented the idea of the solar wind, which was observed by early satellites, and I asked him, a person named Parker, what's his first name? Forget. What did the people who didn't believe in the solar wind and the emission of particles from the sun, what did they say after satellites observed this? He told me they finished their careers still believing it wasn't really there. In other words, people have a certain mindset, and once people are invested enough in that mindset, there's a terrible tendency for them not to change. I mean, it's one of these things where, if we achieve human immortality, one of the biggest risks is that no new idea will ever come up, because it's kind of like people are set in this kind of, this is the way it has to be, and this is the way I have conceptualized it, and it won't change. I have to say, in my own life, I've been lucky enough, I've probably been doing science now close to half a century. And there are things that I have kind of realized have to be the case. And most people are like, no, 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 that couldn't possibly be. Like the importance of kind of, the computational underpinnings for physics. People for decades were like, no, 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 that couldn't possibly be the case. I think now, finally, we're getting to the point where people say, oh, okay, that's probably right. What has gotten us to that point? It's a complicated mixture of kind of ambient thinking about related things, sort of problems with other approaches. Sometimes you'll have the killer experiment that just says, this is it, this is how it works, it has to be that way. But actually, the killer experiment is not as convincing as it often seems to be, like mentioning the solar wind case, where there was a killer experiment and people still didn't believe it. In other words, people can always have, the experiments are hard to do. Sometimes they're incorrectly done at first. Sometimes they validate a theory that turns out to be wrong. Sometimes they validate a theory that turns out to be right. But you can always kind of explain away some parts of these experiments. I mean, we can see that a lot with biomedical research. And I don't know, you go to modern times and, does the vaccine work? Does it not work? Does it do this? Does it do that? All these kinds of things. It's complicated. It's complicated to say, to make the measurements, to make the conclusions, how do you do it? What assumptions do you make? How do you slice the data and so on? It's complicated. And in the end, a lot of these kinds of things are a matter of kind of collective belief, more so than they're a matter of the experiment. I mean, another thing that can happen is that you can have something where the theory, there's a rough edge. There's something about it that we really can't explain, but the theory is so successful that people say, oh, yeah, we believe in that theory, even though there's this nasty rough edge in some corner where people can't really quite explain that, and they kind of wave their hands a bit about that. But the rest of the theory is so compelling and so successful that you go for it. But yeah, I mean, it's kind of a bad story in past times, particularly with sort of, I would say, many religious traditions, particularly, I would say, perhaps, historically in West, kind of the Catholic tradition of, there is a theory of the world and it's what's in the Bible type thing, and that which deviates from it is heresy, and sort of bad things happen to people who are the heretics kind of thing. I think, to be fair, I think that some of the, in my own view, some of these kind of early theological views of the world were more correct than people might give them credit for. They were couched in terms that are very non-modern in the way that they talk about things, but some of the issues and some of the kind of logical conclusions that were made aren't as far off as people might assume based on kind of the layers of centuries of science that came after them. But I think that there was certainly a great tendency to, I would say that if I'm to make a kind of social comment of modern times, the big danger in a lot of times is this forcing of orthodoxy, so to speak. And there is a certain tendency in areas of academia and other things like that to sort of force orthodoxy. And that means that in the light of history, you're saying like, oh my gosh, how could they have missed that? It was so obvious, but the orthodoxy was something different. And there was kind of the societal pressure, the human pressure was such that the thing that was actually turned out to be right in the end was something that was sort of squashed for a long time. And one sees this all over all sorts of different areas of science. There's a question from Jamie here. Is it possible errors in translation have affected results or research? Are there examples of this in history? One fun example that I know is some names, the sine function, SIN, and cosine function. I believe those were, there was the notion of a chord in a circle, piece of a circle where you take the chord, just the line across the circle, and then you have the arc length around the chord. And we still have things like arc sine, but then we have the measurement of the length of the chord. That was kind of this issue of, given a circle, how long is that chord? That was something that was discussed by the Egyptians, and that length of the chord is related to the sine function of trigonometry. But there was a word for it in Egyptian. It was transcribed into Arabic. It was then mistransliterated into Latin. And that's how we ended up with the sine function, which was a mistransliteration of an Egyptian word for chord. And then it was sort of burnt into trigonometry by the 1500s by people like Regiomontanus and so on, who developed what we now consider to be trigonometry, although trigonometry was known to the ancient Egyptians and such like. So that's at least one minor example where that's happened. I think, there are many other kinds of words made a theory type thing. I mean, it tends to be the case that having a word for something is very important in developing a theory. There are words which were intended to be pejorative, so to speak, like Big Bang was a pejorative term for the model of the universe in which the universe started small. There was a much more popular steady state theory of the universe in which the universe was just hanging out there and matter was being added in places around the universe, leading to the expansion of the universe. And it was sort of a pejorative, couldn't possibly be true, Big Bang idea of the universe. That turned out to be the correct idea, as really got sort of ratified when the cosmic microwave background was observed in the early 1960s. So there are cases like that. I'm trying to think about other examples. I mean, one has to remember that the transmission of knowledge went through, a lot of what we now know as science came from, ancient Babylon, the mathematical sciences, ancient Greece, and then it was sort of transmitted a lot through sort of Arab kind of civilization, so a lot got translated in Arabic, survived in the Arabic tradition in monasteries and the equivalent, and so on, and then eventually got translated back into Latin, and came to modern times. And I'm not immediately aware of other cases where somebody goofed by just sort of mistranslating a word, although I bet there were some. Let's see. Aaron is asking, what was the first time anybody considered the angle of our solar system relative to the galactic plane? Well, people certainly knew the Milky Way. The Milky Way, galactos, the word for galaxies, that galaxos is the word for milk in ancient Greek. And so the Milky Way, it's, galaxy milk, that's all a thing. Now, realizing that it was a galaxy, that it was a configuration of stars, and knowing about galaxies other than our own, I believe that was beginning of the 20th century, was where the first observations of galaxies, where the Andromeda galaxy could be seen, and people could guess that that thing we're seeing, that spiral galaxy we're seeing, that's probably the Milky Way that we see of stars that are in the plane of our galaxy, is probably a reflection for us of something like what we see in the Andromeda galaxy. I'm thinking that was an early 20th century kind of thing. And as soon as you know that we are a galaxy, a planar galaxy, then you start saying, well, what's the plane of the galaxy relative to the plane in which we orbit the sun? So I'm guessing early 20th century. Let's see. Pedro asks a question, maybe, why did science evolve so rapidly in the Western world? That's a very interesting question. What were the competitors? I mean, there was kind of the Islamic world, the Chinese, maybe Japanese, maybe, these are all different traditions. They have different traditions of ways of thinking about knowledge. I mean, let's be realistic. Science didn't evolve rapidly in the Western world until the Renaissance. I mean, it was, there was a long period where when people said, we need to know about, we need to know about the world. How do we know about the world? Where does knowledge come from? It comes from the Bible and from Aristotle. Those were sort of two principal books that were used in sort of academic teaching for 1,000 years. And the concept that new knowledge could be created wasn't obvious. The concept that new knowledge was something that could readily happen, and that we weren't really just looking to the ancients for knowledge. That was a thing that that was a real meta realization. New knowledge can be created. Now, that's in what is sort of interesting about that is when it comes to kind of religious belief, that's something where sort of the forces of orthodoxy will say, no, we don't want to create the new. We want to stick with the tried and true, in the case of the Western world, perhaps what's in the Bible. And then, but then we have kind of, we can have modernity and we can have something where we deviate from that. People will say the last 100 years, with Nietzsche's famous quote, God is dead and so on. The key thing that came to be believed is, we don't need any of that stuff that was in the Bible, that stuff that was, religion offered. We can invent everything for ourselves. That's kind of the, in a sense, that's the conceit of modernity. We can just invent everything for ourselves. And that's sort of been conflated a bit with science will invent it for us. We can figure it out with science. Who needs the ancient books to tell us how things work? Well, obviously there are, we see right now in thinking about AI, for example, and here's a very quintessential issue of this type. We're trying to invent AI ethics. We say, great, let's use science to invent AI ethics. Let's make a scientific theory of AI ethics. Well, it doesn't work because ethics is not scientific in that sense. Ethics is not something that has a sort of a necessary formal structure. It's not like something like mathematics where you sort of build it up. Now in the case of ethics, one of the things I've realized recently actually is that one of the features of science is that it allows you to look at subsystems of the world. When we do science, when we look at the science of mechanics, we can say we have this projectile. It is in a vacuum. It's not subject to any external forces. It's moving in this way. It'll obey Newton's second law, let's say. We can abstract away a subsystem from the world. We can discuss this little subpiece of the world and have a scientific narrative about it, independent of everything else that's happening in the world. That doesn't work with ethics. When we say, we're doing one of these trolley problems and we say, do we pick 5 llamas or, 1 rhinoceros? And how do we pick which one will be, which one will we kill with this trolley problem kind of ethical weighing decision? Well, that question doesn't really have an abstracted answer. We could say, well, we can look at the DNA of the llama and the DNA of the rhinoceros and this and that and the other, but that's not really the point. In the end, that ethical question ties itself up with the complete story of what our civilization talks about. It's kind of interesting that in LLM, large language models, the ChatGPT world, that's a case where we are taking the complete sort of story of our language and we're encapsulating it up into this thing. It's very similar to what's happening when we talk about things like ethics and we say we're taking sort of everything that goes on in the world and we're packaging it all up into this one question of 5 llamas or 1 rhinoceros. And I think that's but I think that the traditions of science don't end up saying that much about kind of how ethics works. We can formalize some aspects of ethics, we can kind of use logic a bit, but in the end, ethics is this kind of thing that comes from all the different parts of our civilization, sort of all impinging on that one decision that you're making, very different from science. And so when we ask the question, well, where do we look for our our kind of conceptual foundation for ethics? I don't think we get to say, let's look at mathematical science, for example. That's not a good basis for that. Really, that's a place where we're reflecting back to earlier kinds of thinking, like the kinds of thinking that theologians did for a long time. Theologians were the main intellectuals for many, many centuries. So that's where the intellectual work got done. That intellectual work that predates modern science is some of what's needed in thinking about these very modern questions about things like AI governance and so on. So I think but in any case, that's to say that for a very long period of time, there was a lot of pressure, even in the Western world, to not try and invent new knowledge, because in a sense, inventing new knowledge is to go beyond people thought about it, I don't think it's really a correct interpretation, but to invent new knowledge is kind of to go beyond God, to somehow say we are, we are more than, we are, in the God is dead type quote, we can create for ourselves independent of the kind of the universe that's out there, the kind of the God that's out there, so to speak. We can just invent everything for ourselves. There is no, the humans have triumphed. We can invent anything we want. We don't have to go with the kind of traditions which happened to be written down a long time ago in religious texts and so on, but which were the kind of the long traditions of our civilization. So, what happened in the 1400s and so on, as the Renaissance happened, and what led to that kind of flowering of possibility, I think there are a lot of details that are to do with political history as much as anything else, it probably helps to have some peacetime. It helps to have a certain degree of sort of leisure kinds of things where it isn't the case that everybody at the age of whatever has to go off and fight a war. People can have some chance to kind of just ponder things and so on. But that hasn't been true. I suppose in ancient Athens, for example, it was also a fairly, for good or bad reasons, it was a fairly prosperous place where people could just kind of, lounge around and think about things and debate things. It wasn't like, all hands to the war or all hands to making food. So I think, that helps. I think that this notion of, can one invent the new? Is that something that is part of the cultural tradition? That's a very important thing, and it exists in some cultures, doesn't exist in others. I think it is something that is all too easily extinguished, because I think the natural tendency of our species, particularly when we build larger and larger organizations and institutions, is to force everything in the same direction, to have this kind of industrial flow of things. That's much easier. It's a much easier thing to manage. If you're, let's keep this country under control, much easier if everybody's kind of sort of going in the same direction than if it's like lots of prima donnas all sort of concluding, oh no, actually we'll think about this different thing, et cetera, et cetera, et cetera. So in terms of sort of the societal structure and societal kind of keeping a society from going crazy, yeah, it's a good strategy to just get everything to go in one flow. In terms of inventing the new and making sort of further progress in the world, it's not a great strategy. But I think, I think there've been these few cases where you can see, in Britain, at a time when it had its empire and it was all very, very plush, there was lots of intellectual a lot of intellectual energy sort of started emerging, often on the part of people who, in a sense, didn't have to, quotes, work for a living, so to speak, and could really ponder these more intellectual kinds of things. And there are plenty of examples of people who did do some, work for a living. They worked for the Foreign Office or something in the UK, but they were stationed in some random part of the world, and they studied the local language, the local culture, et cetera, et cetera, et cetera, and wrote lots of things about it and so on, and did what would now be considered sort of academic work on that. But I think this is, it's a feature of it's always this interesting time when the new has happened, when something new has opened up, and then there's the possibility of can that be pursued? And it is a terrible mistake when people say, the new has opened up, let us kill the new. And, that's a way in which sort of intellectual history gets set back by centuries. Now, having said that, we can invent everything, we can do everything, we'll make arbitrarily weird, nasty, I don't know, we'll construct every possible virus, we'll do this, we'll do that, all of these things that, there are things where, or we'll do these things where we let's test this particular hypothesis that, well, yes, it might wipe the species out, but, anyway, we'll test it as a matter of science. Some of these things are obviously bad ideas, And some of the things we can do, there are a lot of issues in sort of ethics of biology and medicine. Do we make the cloned humans? Do we allow, the cloned organs? Do we do these things that will have this effect? Do we have, this and that and the other? There are things where there's a sort of a question, and yes, in principle, we can do these things. Is it a good idea? How does it relate to the global ethics, the full structure of our civilization? That's what we kind of have to be thinking about, and it's something that science has rather little to contribute to. It's not to say that we should just sort of throw science out and ignore it, but one should recognize that there are plenty of things in the world where it doesn't help one terribly much. And this phenomenon that I talk about a lot of computational irreducibility, where you ask the question, given that the scientific rules by which something operates, does that mean you can say everything you need to say about that thing? And the realization of modern times, this is, I started talking about computational irreducibility in 1984-ish. But boy, that's ironic in some ways. In any case, I'd never realized that before. In any case, in the celebration of 1948 that was George Orwell's 1984, and its kind of notions of the structure of that the concept of computational irreducibility should happen to have originated in that year is kind of interesting, because computational irreducibility is the way in which kind of science, from the insides of science, from the hardest science you can get, kind of says science is limited in what it can say. It kind of says there's this sort of irreducible barrier to knowing certain kinds of things in science. And that realization that computational irreducibility is this barrier to knowing things in science, that is not yet understood. It's understood by some people, and I've certainly been yakking about it for 35 years, more than that, nearly 40 years now. And there's some emerging knowledge. I certainly notice among young scientists that I work with that a decent fraction of them take computational irreducibility for granted, even though when I first introduced it, it was like, how could this possibly be true type thing. But it's something where, as that gets absorbed, as the idea that you can know the scientific rules and not be able to predict the outcome, as that gets really absorbed, that is a blemish, a kind of a limitation that one realizes of science, that it isn't the case that, the last 300 years, it's been like, if we can make it into a science, if we can make it into a mathematical type science, we got it nailed, we know everything. Well, no, that's not true. And in fact, from within the science itself, it's telling you that there's that issue. So that kind of makes one a bit more humble about what science might be able to provide. And it makes one a bit more humble about kind of what, we humans can just invent whatever we want and conclude things because science is backing us up. Well, science isn't necessarily backing us up because science is unable to make those statements. It's unable to tell us, no, this sort of system of AI ethics or something is never going to have any problem type thing. So I think that's that's my view of that. Let's see. But this question about when does science evolve rapidly and why did it evolve so rapidly post-Renaissance in the Western world? Fascinating question. And I think there's a lot of coincidences of history, a lot of these moments when there is a fertile moment when things can really advance. You see that it's usually this sort of, usually a methodological advance, some instrumentation, some idea, but it's also can be the ambient sort of environment of society. Is like, we've got new stuff going on now. One of the things that's really interesting about LLMs and the ChatGPT story and so on is this is a wake-up call. New stuff can happen that we didn't expect. And I think that we will see, we've already started to see, but we'll see more of it, of gosh golly, let's re-examine this because something really new might happen in this area. Once there's been one new thing, it's kind of like it almost infects other things with the possibility of newness, so to speak. It's kind of like, there were places where nobody ever did a startup company, but then somebody does a startup company in country X. And then people realize, well, it's actually possible to start a company and to make something from nothing in that way. So I think that's this contagion from one new idea to others is an interesting phenomenon. I don't know how well that's been studied, but I suspect we're going to see that. We are already perhaps seeing that in the kind of AI advances that are happening now. not only is it, oh, let's look at AI, but let's look at all these other things as well, and they may seem less surprising. So Beatty says, what's there to say about alchemy in history? Alchemy turned into chemistry, basically. I mean, alchemy was the attempt to, make gold out of lead, et cetera, et cetera, et cetera, but it was all sort of mixing up things and seeing what would happen, quotes, chemically. And that really turned into chemistry. And, one of the things that happened was there was a certain mathematicization of chemistry that happened in the hands of people like Dalton in the 1800s and many other people, that chemistry became sort of quantitative in a way that it hadn't been. And as soon as we understood about elements and limited numbers of kinds of atoms, that really helped. But, at the time of the alchemists, chemistry was a narrative story of, you stir up this and you do that. It was all words. There was no formalism of chemistry. That's what developed in the 1800s. And that's what allowed kind of modern chemistry to rise out of the ashes of alchemy. Spare Parts asks, is that because ethical questions are fundamentally computationally irreducible questions? I think often that they are. I mean, I think that I think this idea, and I have to admit, I'm only really trying to think this. I've only really sort of been thinking about this recently. This idea that in ethics you can't break off subsystems is an important concept, and that ethics is the story of how everything we think affects what is going to happen. And I think also computational irreducibility and its role in ethics, for example, the trolley problem thing of, the person who invented that problem, Philippa Foot, was a philosopher in Oxford who was actually a friend of my mother's. My mother was a philosophy professor in Oxford. So I'm sure I met the originator of the trolley problem at some point in my youth, but didn't know it. But anyway, this concept of the trolley problem might actually be an ill-formed concept, because it kind of says, oh, you've got this train car and it's going to go this way or it's going to go that way. It's going to kill this thing or that thing. And which way do you want it to go? Well, that sort of denies computational irreducibility. It implies a kind of scientism of, if you push this button, if you move this lever, this will necessarily happen because that is what science says will happen. But actually, it might be more complicated than that. It might be that, well, there are these chickens on one side and there's a dodo on the other side. And, the chickens are such that if the trolley is coming right in their direction, they'll jump out of the way and the dodo won't. And, all these kinds of things where you think it's just you move a lever one way, you move it the other way, what's going to happen. It's a computationally reducible story. But in fact, it might very well be the case that there really isn't, that when you try and do this subsystem reduction thing, which is essentially what the trolley problem is doing, it's trying to take what is otherwise the big entangled mess of ethics where everything affects everything, and it's trying to separate it off into this one specific question, that idea of that separation fundamentally doesn't work. And then how do you do this kind of, because science is about taking what is out there in the world and kind of stuffing it into our minds, sort of slicing it down to the point where we have something that will fit in a human mind and that we can reason about and have a narrative about. So how do you take this thing that fundamentally entangles everything, and how do you kind of stuff it into our minds? I think that's, as I think about it, talking to you guys, that's kind of, in some sense, that can be viewed as a fundamental problem of ethics. How do we get to have principles that are extractable in the subsystem kind of way from this thing that is otherwise just talking about every aspect of civilization? And I think, let's see, maybe one more thing here, and then I should wrap up for today. Tori comments, how do you filter out the good new from the bad new? It's remarkable that old ideas stand the test of time. Yeah, a really good question. How do you figure the good new from the bad new? Sometimes with technology, let's say, there is a sort of de facto, it was a good idea by, look, it made $1 billion company. that's the de facto, it was a good idea. Actually, it may have been a really bad idea, but it turned out that because of forces of various kinds, it may have been an idea that is now, when I say a really bad idea, I'm in a sense entraining some kind of ethical or value system, which I'm not really accounting for. So, it might have been an idea, you could say, well, let's look at, I don't know, some industrial idea. I don't know why I'm thinking of, watches, radium dials that were, radioactive dials and so on, that turned out to be a really bad idea, but they were commercially successful. So you might say that was a good idea, except it turned out to have a sting in its tail that made it a bad idea. But so, this question of what, in the case of technology, a good idea is de facto an idea that is commercially successful. Now, in the marketplace of ideas, intellectual ideas, you could say the same thing. An idea that, a good idea is an idea that takes root and lots of people talk about it. Does that make it, even though in retrospect we may say, I can't believe people had that idea. We take ideas like, I don't know, let's say eugenics, for example, is people look back and they say, I can't believe people had that idea. And maybe that's not even the worst one, because there are ones where it's just I think somebody mentioned here, abiogenesis, the idea that you have a bunch of mud and life can crawl out of the mud, even though there was no life there to begin with. They didn't know about little tiny maggot eggs and things like this. This idea that the living can come from the non-living, or just a whole bunch of these ideas that did indeed persist for a very, very long time. And, I think as a sort of at a personal level, I'm kind of proud of my record, touch wood, I don't know, of not betting on the wrong ideas. I think I have a long record of actually having bet on the right ideas and having not kind of been led too far down the garden path of a wrong idea that nevertheless was popular. I mean, I've been saying, quantum computers as they're defined aren't going to work. I've been saying since 1980. And it's, that not to say that the physics of how you do computing, not with semiconductors, isn't worth doing, and not to say that the formalism isn't interesting, but the actual, look, I've got a branded quantum computer, it really works. There are all kinds of reasons why I don't think that's going to work. And it's not something I'm prepared to bet on, because I'm pretty sure it's not really a real thing. And people will look back and say, oh, that was really they really goofed that up. Maybe some interesting science came up. I mean, it's an interesting thing, like the caloric theory of heat that turned out to be completely wrong, was what led to the second law of thermodynamics, what led to the idea of efficiency of heat engines, what led to lots of things that were absolutely right. So a wrong theory doesn't necessarily have to begat kind of wrong ideas after it. You can have a wrong layer and then the right gets put on top of the wrong. But, this question of how do you tell what's a right thing, what's a wrong thing? I'll tell you, I suppose my heuristic, if I have one, is what were the foundations of that thing? What really are they? And is there a piece of mysticism in the foundations? Is it something where people say, but of course, this or that, we all know this or that. And you say, well, why is that true? And it's like, well, we all know this or that. Very bad sign. And you find that in areas of science. And I had that experience many times of you'll run into sort of a world expert on this or that. And I suppose I'm the obnoxious kind of drilling interrogator of many of these things, kind of, why do we know that? What evidence do we have for that? Well, there's this or that. Does it really show that? What does it really show? And can you drill? What happens when you drill? And my observation is that when you drill, it's solid, it's probably true. When you drill, you end up at the mystical moment, then it's probably not true. Might be true, but you don't really know. And I think that's that, if anything, is kind of a test. But honestly, when people are embedded in a flow of some particular area, nobody drills to the foundations. People are just doing, most of science, for example, consists of people making incremental progress, which is sometimes important, sometimes not so important, that's based on this existing tower that's been built, and people just kind of sort of building the next step on the tower and asking what the foundations of the tower are. That's not for us, is the typical statement of many people in most areas of science. So that means when you don't look at the foundations, well, by golly, they could be really rotten, but you wouldn't know it. And it's not the day job, the daily job of the scientist isn't really to look at that. Often in areas of science, people say, why are you wasting your time on the foundations? That's not what the actual practice of that field is consisting of. Anyway, a lot of interesting questions here. Well, thank you all for that. And I think I must run along, talking of day jobs, to my day job. And I think I'm doing some things to do with LLMs here, talking of modern times and talking of kind of the fertile moment that we're in with respect to AI and so on. All right, well, thanks for joining me here, and see you another time. Bye for now.